Okay, let's work through a slow, careful example showing the steps involved in finding the homology groups. Here's our space S. It's the whole thing inside there. It's given as a cell complex, and I've labeled the cells. So there are our 3 0 cells in a triangle and a 4th 0 cell W down below it. The 0 cells X, Y, Z, and W. There are also 4 1 cells, little a, B, C, and D. Little a happens to be attached. Both of its ends are attached at Z. Then there are 3 2 cells. Capital A and capital B are discs that are glued in to the triangle and the sort of circular teardrop shape there. Capital Q has its entire boundary. It's a 2 disc with its entire original boundary all contracted down to nothing right at W, all to a single point. So you can think of it as a balloon attached there. Okay, so step 1, we need orientation. So I took the same exact space S, but now I've given each of the cells an orientation. Now, that's completely arbitrary, and the arrows do not mean any sort of gluing. Any arrows that meant gluing would have been there in the original picture of S. And if there were arrows that meant gluing, then we might let them do double duty and just assign that orientation as well. But since there was no gluing going on, the entire S was shown as is. I need to assign orientations to all the cells. The 0 cells, X, Y, Z, and W, don't need to be assigned an orientation. They could, but typically we just leave them as is, since their boundary is going to be 0 anyway. Because the reason for the orientation is so that we can find boundaries. Remember, these are the group theoretic boundaries. So it is the boundary as you see it, but it's done as a linear combination with minus signs or plus signs. All the 0 cells, X, Y, Z, and W, have a boundary of 0. The 1 cells, A, B, C, and D, little a, B, C, and D, have boundaries as follows. A has boundary Z minus Z, which is equal to 0, since it's attached at Z. Little b has Z minus X. That's because B is oriented from X to Z, so you get positive minus negative there, or end minus start for little b. Then little c is Z minus Y. Little x is, D is X minus Y. Okay, for the 2 cells, boundary of capital A is C minus B minus D. That's because capital A, we chose the counterclockwise orientation. There's just 2 possibilities to orient any cell, and for 2 cells we can think of them as counterclockwise or clockwise. We chose counterclockwise. That was arbitrary, and then since we chose that, we look at the boundary of A, and the 1 cells that agree with that counterclockwise are going to be positive. That would be C. But then B and D are going against the grain. Their arrows don't point the same way as the counterclockwise rotation around the boundary. So they get minuses, minus B and minus D. Capital B, I chose, just to be different, I chose clockwise for capital B. But that means that my orientation around A is against the grain. It's the opposite of, it disagrees with the clockwise. So it gets a minus. And now Q, I chose counterclockwise. And its boundary, it would look like, is just the 0 cell W. But its entire boundary is there, so it gets a boundary of 0. You can argue that two ways. One is that the boundary should always just be one dimension down. We're not interested in going down 2 dimensions, so it has a boundary of 0. But also, if you glue an entire 2 cell onto a point, it's as if the boundary disappears there and just becomes 0. That's it for the boundaries.